Okay, we're going to be looking at some applications of parabolas. Problem number 1. Jim has 200 feet of fencing and he wants to put a fence around a rectangular dog pen. Determine the maximum area he can enclose and the dimensions of the field. Now, before we start this problem, I want to say that this is one of those problems that is kind of what you would call a classic problem. You learn how to do it in elementary school by making a table of values and just looking at different possibilities. You learn it in college algebra by doing algebra, and then you're going to see this problem again in calculus. The first thing we're going to do is to draw a quick sketch of what we have going on here. And I know this is the width and this is the width. And I know that the length of the two sides, this blue side and this blue side, together have to be 200 minus 2W. Because I start off with 200 feet of fencing, I'm taking away W here and W here. So what's left to cover those two blue sides is 200 minus 2W. So that means that the length of one side is 100 minus W. So I'm going to come up here and label that as well. Okay, now going back to my problem, Jim has 200 feet of fencing. He's going to put it around here. I want to find the maximum area. So I know that area is length times width. So the area is going to be 100 minus W times W. I'm going to distribute. Okay, I have the W squared, which means I have a quadratic. And we're normally used to having our quadratics in terms of x's and y's, but that's okay, it's still a quadratic. So I'm going to put this in standard form. Now, what we are going to be thinking about, we are thinking about this as y equals negative x squared plus 100x. That's kind of what we're relating this to. I'm going to draw a quick sketch of this parabola. Now, because we're dealing with area here, we only need to be looking at a graph in the first quadrant. This is a parabola that's going to be opening upside down. I know that because that leading coefficient is negative. The horizontal axis is representing the width, the vertical axis is representing the area. So if I want the maximum area, I'm looking for this vertex. So how do I find this vertex? Well, remember the x-coordinate of the vertex is negative b over 2a. So that's going to be negative 100 over 2 times negative 1. So that's going to be 50. So the x-coordinate of this vertex is 50. Okay, to find the y-coordinate of the vertex, I'm going to find f of 50. So put 50 in place of w, and we get 2,500. So I'm going to label this over here on my graph. So the maximum area is 2,500 square feet. Just real quick here, I want to talk about another way I could have done this problem. Once I found the x-coordinate of the vertex, I could have gone back to my original diagram. And I know that this is 50, so this is 100 minus 50. So this side is going to be 50 as well. So the area is length times width, or 50 times 50, which is 2,500. Anytime you have a problem like this with a rectangular area, the final answer is going to end up being a square. Okay, now problem 2 is a little bit different. A farmer has 120 feet of fencing and he wants to put a fence around a rectangular field on the south side of the barn. The fence will only be needed for 3 sides and determine the maximum area he can enclose and the dimensions of the field. Okay, so to have my picture of what's going on here, I have a pin on the south side of the barn. So here's the barn, and this is going to be the width. This is going to be the width. And this length right here is 120 minus 2W. Because we have 120 feet of fencing, I've used W over here and W over here, so what's left is 120 minus that. Now this problem is not going to be a square. Remember last time I said that all those problems with maximum area are going to be a square? Well, they threw a little twist into this problem where it's not going to be, and that's because we only have 3 sides of fencing, because this side up here at the top is actually the south side of the barn. Okay, so just like before, we're going to find our formula. Area equals length times width. So the area here is going to be 120 minus 2W times W. Distribute. And then switch this around. Let's put this in standard form. Now, you really don't need to do this, but I like to do that. And we have this parabola that's opening upside down. This is the width, this is the area, and I'm trying to find this vertex up here, which will give me my maximum area. So I want to find the x-coordinate, or the W of that vertex. So negative b over 2a. And that's going to be negative 120 over 2 times negative 2. And that's 30. Now I need to find f of 30, so I'm going to put 30 in place of that W, and that's going to give me 1,800 square feet. And that's my final answer. Okay, problem 3. A projectile on Earth is shot straight upward with an initial velocity of 40 meters per second. The height s in meters is given by this function, where t is the number of seconds after liftoff. This s of t right here is a distance. Don't let that s of t throw you. It's really just like f of x. What we are going to be doing first of all is making a quick sketch here so we can understand what's going on. I have a parabola here that has a negative coefficient, so it is opening upside down. So my graph is going to look something like this. My horizontal axis is time, and my vertical axis is s of t, which is my distance. The question is, after how many seconds does it reach its maximum height? So I don't really care what the height is. I want to know what time it is to reach that maximum height. Well, I want to know that x value, if I was looking at this in terms of x's and y's, so I want to find negative b over 2a, the x-coordinate of that vertex. So negative 40 over 2 times negative 4.9. And that is approximately 4.1, so 4.1 seconds. Next question is to determine the projectile's maximum height and round your answer to the nearest tenth. Well, to find this height of this parabola, it's the y-coordinate of the vertex. So I put 4.1 into my function, finding s of 4.1 is negative 4.9 times 4.1 squared plus 40 times 4.1. And that's going to be approximately 81.6 meters. Now, one thing I want you to know is that some of the problems in my math lab may not ask you to do this first part up here. They may just ask for this answer right here. So you will have to do this part. You will have to find the negative b over 2a in order to get to this question, but they just may not really care about that answer. Okay, last part. How long will it take until it hits the ground? Let's write down our function again. Okay, remember this s of t is the height of the object. So if I want to know when it hits the ground, that means the height of the object is 0. So 0 equals negative 4.9 t squared plus 40t. Okay, so now I have a quadratic that I can solve. I'm going to factor out a t, set each factor equal to 0, and solve. I have two answers here for t, 0 and 8.2. T equals 0, it means time equals 0, so that means when this starts, the height is 0. And then at 8.2 seconds, the height is also 0. Okay, problem 4. The number of tickets sold in millions to the top 50 rock concerts in the years 1998 to 2002 is modeled by this function, where 1998 is represented by x equals 0. In what year was the maximum number of tickets sold? Okay, I'm going to draw a quick sketch here of my graph. Okay, so I want to find the maximum number of tickets. So I want to find the x-coordinate of that vertex. So negative b over 2a, and that's going to equal 3. Now, my answer is not the year 3, right? Because this x of 0 is representing 1998. So it's 3 years after that. So I have to add 3. So I get the year 2001. And the second question is how many tickets were sold that year. Now, I do have to go back to that 3 to plug into my function. And the answer that I get here is 3.5. But this is not 3.5 tickets. Remember that this is in millions, so this is 3.5 million tickets.